Thank you very much for the kind invitation. Can everyone hear me? Should I speak louder? Good. So, I realize that not everyone here is a cryptographer. Actually, I assume that most of you are not. So I prepared a talk which will start from the basics, and I will try to give you the flavor of the very latest research results. Some of them haven't been published yet, from the last few months. Occasionally, I'm going to talk about things which are a little bit more advanced, so I'll warn you in advance. If you're not an expert, you might lose me here, but then you'll be able to rejoin later. So I'm going to give a talk about how crypto systems get broken in practice. So in theory, let's start by a definition of what is a crypto system. So for those of you who have never seen a crypto system, some of the sizes do not fit here. So sending a plain text securely from Alice, the sender, to Bob, the recipient, is done in the following way. You have a box which performs the encryption. The encryption takes the plain text, for example, good morning, etc., mixes it with a cryptographic key, and generates a ciphertext that looks very, very general, random looking. This is sent over the communication line to the decryption box owned by Bob, and Bob is going to use the key in order to decrypt it and read again the good morning here. Now, in public key scheme, the two keys are not the same, but this is a slight point that we'll ignore here. So we'll talk about a key for the sender and the key for the recipient. Now, what is the mathematical way of viewing a crypto system, of thinking about crypto system? We think about them as mathematical black boxes. Namely, a crypto system is just a function which has two inputs, a plain text and the key, and one output, which is the ciphertext. The security of a crypto system is a mathematical theorem which you are trying to prove. So you say, this crypto system is secure because I can reduce the security of the crypto system to some well-studied problem in mathematics, to some NP-complete problem, to the difficulty of factoring, something that we trust in. We usually think about Alice and Bob not as human beings, but as interacting Turing machines. So each one of them has a program, and it is running the program, and is not supposed to deviate from it. And even the cryptanalyst, the bad guy who is trying to break the crypto system, is doing only what he is supposed to do. So if we allow him to access the ciphertext, but not the plain text, this is what he is going to do. We make all kinds of assumptions about the power of the cryptanalyst. So here is the picture. The cryptanalyst is assumed to always have access to the ciphertext. So if he needs 1 million ciphertexts for the cryptanalysis, that's okay. He will listen to all those ciphertexts and write them down and analyze them. We also allow the cryptanalyst, in many cases, to access or choose the plain text. So he might say, it's difficult for me to break the crypto system in general, but if you tell me what was the plain text corresponding to the first ciphertext and the 10th ciphertext, it will be of great help. So we allow the cryptanalyst also access to some of the plain text. And in even stronger kind of attack, we allow the cryptanalyst to choose the plain text. So he can ask Alice, please encrypt the message 0000 for me and tell me what is the result. And now please encrypt the message 111000 and give me the ciphertext. So he can use a chosen plain text attack, and he can also try to choose a chosen ciphertext. He can choose a chosen ciphertext and ask it to be decrypted, and then he gets the message. The point is that after all these preparations, he should be able to discover what is the cryptographic key used in the encryption. Now, this kind of mathematical cryptanalysis, where the cryptanalyst has access only to the ciphertext and in some limited way to the plain text, is the classical method which had been studied, and it was quite successful in many cases. Perhaps the most successful attacks of this type happened during the Second World War. You know that Alan Turing in the UK and William Friedman, who worked for the predecessor of the NSA in the US, managed to break the German Enigma code and the Japanese Purple code. So actually, they could read most of the communication between Hitler and the troops in the field, or between the German generals and among themselves, and also they could read the diplomatic code used by the Japanese and the Navy codes used by the Japanese Navy. So the fact that the British and American had such direct access to the most secure communication of the German and Japanese led to many of the successes in the Second World War. For example, the main reason that the British Royal Air Force managed to stop the German Luftwaffe bombing of Britain was because the British knew exactly when the attacks will be coming, which target will be bombed, how many airplanes will participate, so they could locate their few airplanes in strategic locations in order to intercept the German bombers. So they suffered heavily, but they stopped the Germans from defeating UK in 1940 when the UK was alone opposing Germany. Now, something which might be closer to home, you know that this code breaking almost succeeded in stopping the Japanese bombing of Pearl Harbor. This is an amazing story. So the Americans actually knew about Pearl Harbor in advance. But it was peacetime, and what happened was that the Japanese Foreign Service in Foreign Ministry in Tokyo sent a very long telegram in 13 parts to the Japanese embassy in Washington, which included the declaration of war. And because it was so long, it included the historical perspective. They talked about the relationships between Japan and the US in the past. So the first 12 parts took many, many hours to transmit from Tokyo to the embassy in Washington. And it took many hours to transmit, and the Americans were reading it as it was transmitted, but there was no sign in the first 12 parts that a war is going to break out. And only in the last 13th part of this long document, the Japanese concluded by saying, and therefore we declare war on the US. If the Japanese, and by then it was only half an hour before the actual attack, it was nighttime in Washington, everyone was asleep, so the fact that an attack is coming within half an hour was lost, and the Americans were not ready. If the Japanese had included, we are declaring war on the US in the first part, and not in the last part of this very long telegram, the Americans would have stopped the Japanese attack on Pearl Harbor, and as a result, the war would have ended in a year or two, instead of taking so long in the Pacific. But after this bad experience in December 41, the Americans knew what they should do. So half a year later, the Japanese, who destroyed all the battleship in Pearl Harbor, they didn't manage to destroy the American aircraft carriers because they were out of Pearl Harbor on maneuvers. And the Japanese Navy decided to have a major naval battle at the island of Midway, halfway between Japan and the US, in which they wanted to destroy the American aircraft carriers. If they had succeeded in this, the war could be won by the Japanese. But the Americans broke the Japanese code. They knew exactly where the Japanese Navy was going to, and from a maximal distance of several hundred kilometers away, the American aircraft carriers sent all their aircraft to the exact location where the Japanese Navy was, and they bombed and torpedoed the Japanese Navy, and as a result, the relationship between the badly hurt American Navy and the proud Japanese Navy, very powerful one, was now equalized. Both sides lost half their navy. And from then on, the American industrial power enabled the Americans to build many more ships than the Japanese, and the Second World War was decided in the Pacific. So you see that this kind of mathematical cryptanalysis played a major role in the history of the world. Now, modern crypto systems, which were developed over the last 20 or 30 years, seem to be immune, cannot be broken by such mathematical attacks. So I can give you examples. The advanced encryption standard, that's a famous block cipher, was developed in the late 1990s. It had been studied very, very intensively by military people and the academic researchers for the last 10 years. Still, we haven't managed to break it. If we look at the RC4 string cipher, this is a method that was developed by Ron Rivest in the late 80s, so it had been studied for 20 years and it is still not broken. If we look at the RSA public key crypto system, it was developed in the late 70s. We have been studying it for 30 years and we didn't find any mathematical attack on it. There's one exception of a famous crypto system or cryptographic scheme which had been broken, and of course this is the breaking of SHA-1 by Professor Wang, who managed to, and her team, who managed to find a very interesting mathematical attack on a major scheme that was not broken for many years, for about 15 years. Now, is it possible to break the security of communication systems which use those very, very strong crypto systems? I mentioned RSA, I mentioned AES, I mentioned RC4. So, if the crypto system is strong, can the cryptanalyst do anything? Well, the answer is that, yes, crypto systems are broken all the time. Secret communication is revealed all the time, but not by the same kind of mathematical cryptanalysis that happened during the Second World War. Today, crypto systems are broken typically by totally other techniques. So let's try to look at some of those techniques. So, in general, a communication system for secret data is a complicated system, has many parts in it. And in any chain, you know that the strength of the chain is only as strong as the weakest link. But cryptography is usually the strongest link in the chain. That's not what you should try to break. You should try to break other parts. So attacks usually violate the black box assumption that I mentioned to you, and I'll give you now many examples about how to find ways how to bypass the strong cryptographic protection and still read secret communication. So this difference between the strength, the mathematical strength of crypto systems we use today, and the fact that we can break communication systems in many cases is summarized by this nice drawing about, in theory everything is nice and strong and beautiful. In practice, there are all kinds of compromises. So here is an example of an unfair attack. There is a crypto system, and the security of the crypto system depends on the key being kept secret. So let's break the security by stealing the keys. Okay, so the cryptanalyst earlier was supposed only to listen to the ciphertext or occasionally choose or know the plain text, but here we'll go directly after the keys. Okay, how can we do it? Well, there are many ways how to steal keys. So classical examples, during wartime, one military usually captures crypto systems and captures operators of crypto systems and captures code books. So during wartime, lots of crypto systems and their keys are lost. And one of the first things that happens, for example, when a submarine like the U-571 sinks, immediately a party of sailors is sent in order to try to recover the cryptographic keys which are kept in that submarine. And the submarines usually keep the keys for the next few months of operation. And this greatly helps. I don't know how many of you have seen, there's a famous movie, U-571, it describes exactly this story. Espionage. So, the most famous case was the Walker family of spies. It turns out that the American military person who was in charge of hand-delivering cryptographic keys to the 7th Fleet, the American Pacific Navy, was employed by the Russians. And he got millions of dollars for his services. And whenever he was asked to deliver a cryptographic key from the Navy headquarters in Washington to one of the American ships in the 7th Fleet, he was making a copy of it and giving it to the Russians. So without doing any cryptanalysis, the Russians were able to read more than 1 million top secret cryptographic codes. And it turned out that it wasn't only Mr. Walker who was doing it, but all his family members were employed by the US Navy, and all of them were spies. One of the biggest disasters in American security. This happened in the 1970s. Dirty tricks. Keys are sent by diplomatic couriers, are kept in embassy safes. CIA and other organizations usually try to steal those cryptographic keys from diplomatic pouches. Trojan horses. When the FBI suspects that someone is involved in crime, in child pornography, in dealing with drugs, many of those people are encrypting data on their home computers. The best way the FBI has, in order to break the security of those files, is to implant some Trojan horse or virus or some kind of bad program which could be sent over the internet, or the FBI occasionally breaks into the home of somebody and actually puts this software on the target's computer. So this will, sometimes they put a keylogger between the keyboard and the computer, a very small piece of hardware which records all the keystrokes. So if you type in your password, it will be captured by that device. Now, one of the most famous ways in which crypto systems were broken by stealing the keys happened in the case of the Swiss company Crypto AG. Crypto AG was one of the two most famous Swiss companies that manufactured crypto systems during the 1980s and sold them to dozens and dozens of governments and military organizations. So because they were a famous Swiss company, people tended to trust them that they are making good crypto systems that are going to protect data well. What it turned out, this was a big scandal when it broke out in the early 1990s, was that this Crypto AG company was secretly owned by the American Secret Service together with the German Secret Service. And they actually made crypto systems that looked very strong, but in fact revealed their keys. So the way that tempered crypto systems operate is the following. So if this box was made by Crypto AG, it is sending out the ciphertext, but along with it, in a secret way, it is also sending the cryptographic key. And there are many ways how you can do it, by changing the timing and changing, making small errors which are corrected by the error correcting code, but the location of the error bits tell you what the cryptographic key was. So you secretly reveal the cryptographic key. So the cryptanalyst listening to this line is not faced only with the problem of decrypting the ciphertext. It is getting the actual key, which makes life very, very easy. This is a real-life story. Now let me describe to you a new technique which was developed only 2 months ago, how to steal cryptographic keys from devices, like laptops. So this is a method that was developed by Ed Felten from Princeton University. And you can find many details about this if you search for the internet. Use baidu.com. So look for cold boot and Princeton, so you'll find it. So let's assume that a military organization or a diplomat or a police officer has a laptop which has a lot of sensitive data on it. Since laptops are lost and stolen all the time, everyone recommends that sensitive information kept on the hard disk of laptops should be encrypted. Because if you don't encrypt the data on the laptop, anyone who steals the laptop will be able to read all the files in your computer. So if you look, for example, at Microsoft Vista, you know that part of Microsoft Vista is a new technology which is called BitLocker. BitLocker is a disk encryption utility which operates in the background. Every time you write into the hard disk, it encrypts the data, and every time you read from the disk, it is decrypted so you can see the original data on your screen. And there are at least 10 or 20 other companies which are selling disk encryption technology, and that's what is used by all the military and diplomatic organizations when they have sensitive information on laptops. Okay. Let's assume that the crypto system used is very strong, the Advanced Encryption Standard, AES. We have no idea how to break AES by a mathematical attack. Now, when the laptop is stolen, it is usually in sleep mode because it's stolen from a hotel or from a restaurant or from the backpack of someone, and it is not running, it is in sleep mode. In sleep mode, the computer will require a long and complicated password in order to, or maybe even pressing your finger for biometric checking, in order to know that indeed it is now turning on in an authorized way. So if I take the stolen laptop and I try to turn it on, it will ask, do you know the password? I'm the attacker, I don't know the password, so how can I decrypt the data on the hard disk? I can take the hard disk, put it in another computer, but it's encrypted. I'll not be able to break the encryption. So what can we do? So if you look at how the sleep mode works, actually all the data, all the operating system, and everything needed in order to run the computer is still stored in the RAM, random access memory. The RAM is volatile in the sense that if you disconnect it from power, it loses the data. It does not keep data without power. And if you are going to turn off the computer, or if you wait too long and the battery runs out on a sleeping laptop, you lose all the data which was in the memory. But the memory will contain somewhere the cryptographic key which is used in order to encrypt data on its way to the hard disk and to decrypt the data coming back from the disk. This is part of the operating system, so somewhere in memory is the key. Our goal is now to steal it from a sleeping computer. Is it clear what I'm going to do now? So, the new technique that Ed Felten, that's not my result, that's Ed Felten's, is the following. He made a very simple observation. I said that data is lost in RAM if you turn off the computer or if it is the battery runs out. But that's not exactly correct. Data can be kept alive in unpowered RAM for tens of seconds if you just cool it to sufficiently low temperature before you disconnect power. So let's look at what you do. The data will deteriorate over time. So if you unpower the computer and wait for a day or a week or a month, the data will be lost. You will not be able to recover it. But if you only want to unpower the computer and access the data 30 seconds later, 60 seconds later, much of the data will still be there, provided that the memory chips are cold enough. So here is the technique that he actually experimented and showed works. Here is the stolen laptop. You open up the box, and here is the memory module. You take something which is called Quick Freeze. It's a small spray can. You can buy it for $2, very cheap. You spray it, and it cools it down to minus 20 degrees, or minus 30 degrees. Very quick cooling down, which is easy to do. If you want a close-up, looks frozen, right? Now, it turns out that at this temperature, the data can be kept for a minute, maybe 2 minutes, but with errors. Errors will start appearing almost immediately, but much of the data will still be there. If you want to keep it for longer periods, use liquid nitrogen. That's minus 193 degrees Celsius, and this will keep it for maybe an hour. So you first quick freeze it to minus 20 degrees, then you take out the memory module, then you put it in liquid nitrogen, and then you can sit for an hour, and nothing will happen to the memory. Now, the best way to demonstrate the slow deterioration of data is the following. Here is the Mona Lisa. After 30 seconds, the picture looks like this. And because there are different banks of different chips containing different banks of memory, some pieces deteriorate more and some pieces deteriorate less. So, still very recognizable. If you wait 60 seconds with unpowered RAM, which is cold, if it's done at room temperature, it will lose data immediately. At minus 30 degrees, after 60 seconds, it's still recognizable, but lots and lots of data is lost. So, how to overcome all the known types of disk encryption, BitLocker and TrueCrypt, and there are similar things by Apple computers. So, after cooling the RAM chips, you turn off the computer and immediately turn it on after inserting a small and very fast operating system, not Vista. Use a really fast operating system on a disk on key. You know that laptops can boot from disk on key. So it will take only 5 or 10 seconds for the boot process of a simple operating system, and now the computer is running with a very simple operating system which allows you to read memory, and now you can dump the whole contents of memory into the disk on key. And now you have all the time in the world to try to find the cryptographic key inside. But you have a gigabyte of data. Somewhere there is a cryptographic key of AES. How do you know where it is? It's very difficult to find where the cryptographic key is located. So what you do is, you know that somewhere there is a slightly corrupted version of AES. But for those of you who know how AES operates, AES is usually not kept as 128-bit key. It is first expanded into 10 subkeys, each one of size 128 bits. And each one of those subkeys is used in one round of AES. So the important thing is that the original 128-bit is random. There's no structure. But first you expand it into 10 subkeys, which are related to each other in a very strong way by the key expansion procedure. So this now becomes a good error correcting code. If I look at a region in memory and say, could this be an AES key, I check whether the successive parts of size 128 bits are related to each other as expected by the key expansion of AES. If they have the relationship, I say, aha, that's the AES key. So for those of you who don't know how AES operates, it might be a bit too fast, but we are using the fact that the key was expanded before the encryption, and then it will be uniquely defined somewhere in memory, and even if 20% of the bits are wrong, because of the expansion, you'll be able to correct all the errors that will be introduced by the imperfect cooling. So that's a very beautiful technique, and it was shown to operate and to defeat all disk encryption techniques. So if you lose your disk, your laptop now, don't rely on the security of your disk encryption technology. Okay, how to protect the data? Some people suggested using a method in which you prevent the access by the cryptanalyst to the ciphertext. So we said that the starting point of the cryptanalyst is that it should have access to the ciphertext, otherwise it cannot do much. So let us make sure that this line is unavailable. In what sense? We will make it either impossible or we will make it evident that somebody was accessing the ciphertext. So we need tamper resistance. We need something that will trigger an alarm if somebody is reading the data going between the sender and the recipient. How can we do it? You see, if there was a radio transmitter and the radio receiver, and they were communicating over radio waves, you cannot prevent someone from listening in. If this is a fiber optic line, 20 years ago people thought that it's very difficult to eavesdrop to the communication on fiber optic lines. But you know, the Americans have spent about $1 billion on building a special submarine which has a special room in the middle that can lift fiber optic lines from the bottom of the ocean and splice it and put reading devices in. So the Americans have the technology to read communication on fiber optic lines without too much difficulty. So it's very difficult to prevent someone from accessing the ciphertext. But let's try to make it clear that someone was doing it. And this will give us a warning that someone is tapping the line. Someone is listening to us, and then we will not send important messages on that line. So this idea is based on quantum cryptography. It's actually a fairly old idea. It was invented in 1984 by Bennett and Brassard, and it was claimed to have a full mathematical proof. Namely, by the laws of physics, no one will be able to eavesdrop to a line protected by quantum cryptography without raising the alarm that somebody is listening in. How does it operate? And by the way, there are at least two companies which are trying now to commercialize this technology and to actually sell such devices. They have demonstration systems that can communicate the distance of up to about 30 kilometers and using the laws of quantum physics. So here is the basic idea how quantum key distribution, quantum cryptography operates. You have a box belonging to the sender. It has a light-emitting diode or a laser which sends out only one photon of light, very, very weak pulse of light. That single photon is going through a polarizing element. That's a polarizer, like in sunglasses, which polarizes the photon in a particular direction. And if the photon is in the wrong direction, it will stop it. If it is in the right direction, it will let it through. And this polarizer can be rotated to any one of four particular directions. It could be vertically polarized, horizontally polarized, diagonally polarized like this, or diagonally polarized like that. Now, the receiver has a similar box, also with a rotating polarizer in front, and a very, very sensitive photodetector, a photomultiplier typically. So if that single photon is going through, it will be detected and create a pulse. Now, the attacker is sitting in the middle. And remember that only one polarized photon is going through. Now, the point is the following. The sender chooses at random one of the four possible directions of his polarizer. He doesn't tell the recipient which direction he chose. He sends that single polarized photon, say, once a second. Every second, he rotates the polarizer in a new random direction, sends a photon. Then rotates it in a new random direction, sends a photon. The mechanical polarizer, say, need half a second to rotate. So you send it once a second in order to give time for the rotating polarizer to get to the new state. Now, a few milliseconds before the next photon is sent, the sender is already set to its new orientation. Okay, so I know that every second, on the second, a photon will be sent. The attacker has physical access to some intermediate point on the fiber optic line, but the attacker cannot try to measure the passing photons. Why? Because the trick is that the secret information which is sent from the sender to the recipient is the direction of the polarization of that photon. Now, if you try to measure the direction of the photon measuring in the wrong direction, then you are going to actually influence the polarization of that photon by the laws of quantum mechanics. You cannot perform measurement without interfering with the measured element, with the photon that you are measuring. So every time you try to measure the polarization of the photon, you actually rotate it. Now what happens in this scheme is that the receiver doesn't know in which direction the sender was polarizing. So he is measuring in random directions. The photon is sent, this polarizes is vertical, this happens to be chosen in horizontal direction, the photon doesn't go through, okay, he records that he didn't get any photon. Then next time, this is trying a diagonal direction, and this will try again the same diagonal direction by chance, and as a result, he will receive a photon in that direction. What happens at the end is that after sending and receiving all the photons, they compare notes. They say, in which direction I sent photon number 17, and in which direction the recipient tried to measure it. And if they know that they happen to be the same direction, they check whether indeed they got the photon correctly. And any attempt to listen in and to perform measurements on the photon in the middle will create too many errors in which the sender polarization, the receiver's polarization were the same, but the photon didn't go through because it was rotated by the guy in the middle. So that's the principle. Now, can you break it? The answer is, so there is a mathematical proof that you cannot break it. You say, we know from physics that any attempt to measure will create errors. The two parties will notice that there are too many errors, so they know that somebody was eavesdropping. How can you break such a scheme? So here is the idea that I came up with. I didn't publish it, but I told those two companies and some of the researchers working in the field that it's very easy to break their scheme. Here is how. Remember, the attacker has physical access here. Instead of trying to measure the single photon which is going through from sender to receiver, the attacker will actually send a strong pulse of light with many, many photons upstream, backwards, towards the sender. And he will do it a few milliseconds before the real photon goes forward. So let's try to understand what happens if you shine a strong pulse of light backwards. It will go through the fiber optic line, go through the polarizer, which is already set to the correct angle, say diagonal. It will be reflected internally, because it's not a perfect black box, and some of it will go again through the polarizer and come out. So the attacker will measure the direction of the polarization of his own photons, not of the single photon that will be sent later. He is measuring the direction of the polarizer before it is actually sending the single photon. So you know exactly in which direction all the bits are sent, and you can break the security of the system. So you see, this is the kind of indirect way in which you can break very strong crypto systems by thinking out of the box. Okay, let's move now to another topic, and this is the gray box view of cryptography. And this is different than the black box approach. Remember, earlier this was a black box, now it is gray box. In a gray box, the cryptanalyst can see through. He doesn't see clearly, but he can see some things which are happening inside the encryption device or inside the decryption device. So how can we get some information about the processes going on here. There are many techniques. For example, he can try to use a sensitive antenna and amplifier to pick up electromagnetic radiation coming from this encryption device. This is called the tempest attack, and all modern crypto systems are protected against tempest attacks. There are some standards how to electromagnetically shield every sensitive piece of information. Now, another technique is to measure the power consumed by the encrypting device. So this, for example, could be a smart card which is doing encryption. The smart card doesn't have any internal battery. The power is provided by the user of the smart card. And if the user of the smart card is the cryptanalyst who tries to break the security, he got a smart card, for example, for a telephone company, for GSM telephony, the SIM card. So he will give power to the card and measure very carefully what is the power consumed by the smart card when it is doing encryption. So, in general, if there is a PC which is located in some secure office, and you, as the cryptanalyst, want to attack it by what's known as a lunchtime attack. What's a lunchtime attack? You have just a few minutes in which the office is empty, somebody went to buy a sandwich, the computer doing the cryptography is there, you have a few minutes to access it, and you have to find out the cryptographic key in a few minutes. You don't have infinite access time to this PC. So, how can you measure the power consumption of a secure PC which is running in an office which is unoccupied for a few minutes? You cannot take it out of the wall and connect a measuring device between the PC and the socket in the wall, because this will turn off the computer, it will stop doing cryptography. You cannot open the enclosure, it might be sealed, it might take too long. So I thought about it together with one of my students, and we came up with a very simple solution. Most PCs are coming now with a USB plug, so you can connect USB to them. Now, the USB allows you to communicate data between the disk on key, the external device, and the PC, but it also supplies power, 5 volts, to the device. Let us measure carefully the voltage on the power pin of the USB connector. So, many security programs, if you are running a secure PC, they disable the USB connector because it might be too dangerous for somebody to steal data from the computer and load it into a USB. So we looked at some of the commercial USB disabling programs. What they do is they turn off the USB driver in the operating system. But the USB power is still on. The 5 volts is still there. You only prevent data. Data cannot be sent back and forth, but the power is there. So those security softwares will not save you. So here is an example. What we did was we measured this is in the frequency domain. This is the frequency in kilohertz, 100 kilohertz, 200 kilohertz, 300 kilohertz. So it is the spectrum of the 5 volts, nominal 5 volts, available on the USB connector. Now, the blue is when you are running encryption of OpenSSL encryption, and the green is when the computer is not running the encryption. And you see that the frequency spectrum is very different when it is running the cryptography in OpenSSL and when it is not running the cryptography. In particular, there is this peak at around 294 kilohertz, which is a very strong signal that the PC is now running OpenSSL. Now this is, of course, typical to a particular PC that we're running our experiments. Another PC will have another peak. But once we discover a peak which characterizes only the OpenSSL operation, what we can do is look at the real-time signal in a very narrow bandwidth around 294 kilohertz. So you see that you get almost no signal before the OpenSSL encryption starts, and then you are doing RSA encryption starting exactly at this point, ending here. So it is very, very noticeable, first of all, how long the operation took. This leads to timing attacks, and also you get the exact power consumption without all the peripherals and other programs running, making it too noisy to analyze. So now that we have an easy way to measure the power consumption of a PC, or you could do it also on smart cards, of course, even easier, how can we use them in order to break RSA cryptography? So here's a new technique which was developed by me together with a couple of researchers from Japan in the summer of 2007, so less than a year ago. So to decrypt ciphertext or to sign messages in the RSA crypto system, the device, PC or smart card, computes X raised to some secret exponent D modulo a number N, which is the product of two large prime numbers, P and Q. For those of you who have seen RSA, this should be trivial. For those of you who have never seen RSA, this might be too complicated. But let me try to lead you through the basic ideas of the attack. So you have to raise the input X to a very large secret exponent D. If you find D, you have broken the security of the scheme. The problem is, how can you find to which power you raise the input? So because D is so large, in order to raise X to such a large power, we usually do it by a sequence of squaring and multiplying. So here's a concrete example. If you want to calculate the input X raised to the power 25, you don't do it by X times X times X times X 25 times. This will be too long. Instead, you calculate X squared, and then you multiply it by X, so together it is X cubed. Then you square it, it becomes X to the 6. Then you square it again, it becomes X to the 12. Then you square it again, it becomes X to the 24. And then you multiply it by X, it becomes X to the 25. So the whole operation of raising to the large exponent D can be summarized by, first I do a squaring, I call it S, and then I do a multiply by the input X, I call it M for multiply, and then I do a square, and then I do another square, and then I do another square, and finally I multiply. So anyone who knows the sequence of S and M can know what is the exponent D. So my goal is to find what is the sequence of operations of either squaring or multiplying. Okay, let's see how to do it in a very, very easy way. I'll show you how to do it with two messages. So in the past, people implemented the squaring and the multiplication by very different algorithms, and you could just look at the power consumption curve and see that squaring was a faster operation, so it took less time. Multiplication was a longer operation, and just by looking at how much time it took, you could determine it. So all the modern implementations of RSA use exactly the same algorithm for squaring and for multiplication. You don't do any shortcuts. Basically, you take a very long number, and to multiply it by another long number, you multiply every word from input 1 by every word from input 2, and multiply and add in the usual way. So there are known techniques how to do power analysis, but they require a very large number of messages and sophisticated signal processing. I'll show you a much easier way. This is how the power consumption curve looks like. It's a very crazy wiggly line, and it depends on exactly what is the Hamming weight of the value that you are now writing into memory. If it has many ones, it consumes a little bit more power. If there are few ones, it consumes slightly less power. When I multiply two numbers, again, how much power is consumed depends on how many transistors are switching state. So very, very complicated operations, and it's not clear. You see, here it was a squaring. Here it was a multiply. Here it was a square. But looking at the power consumption curve, you will not see any difference, because most of the difference depends on exactly which numbers you multiplied, and not on whether you multiplied a number by itself or a number by a different number. This is very difficult to distinguish. So, here is the idea. I'm going to ask the device to perform two exponentiations of two messages. Now, when I'm comparing the two power consumption curves, when I'm exponentiating input x1 or when I'm exponentiating input x2, I'm going to use the power consumption curves as a kind of oracle in the following sense. If we multiply a times b when I do one exponentiation, and I perform another multiply of c times d in the other exponentiation, then if a equals c and b equals d, it means that I was doing exactly the same multiplication in both exponentiations. I multiplied 5 times 7 here, and I multiplied 5 times 7 there. Exactly the same number of transistors switch state, the same numbers are written into memory, so the power consumption curves look identical. If A is equal to C, but B is different than D, for example, I multiplied 5 times 7, and compare the power consumption curve to the multiplication of 5 times 11, they will not look similar. They look very different. So, we ask the smart card or the PC to exponentiate the two numbers x and minus x, modulo n. Minus x is the number actually n minus x. The binary representation of minus x looks very, very different than x. So x is 0, 1, 1, 0, 1, 1, 0, 0, 1, 0, and minus x looks 1, 1, 0, 0, 1, 1, 1, 0, 1. Totally different looking numbers. But these are the two numbers that I'm asking to exponentiate. Now, consider the particular sequence SSM, square, square, multiply, square, multiply, square, 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 multiply, etc. By the way, there's always only one m between s's. You never multiply followed by another multiply. Between every two multiplies, there's always at least one s, but maybe more than one. Now, when I exponentiate x and minus x, the input here to the first squaring operation is different. I squared number x, I squared a totally different looking number minus x, power consumption curves look different. But after the first squaring, the difference between x and minus x disappears, because x and minus x squared are the same x squared. Minus squared is 1. And therefore, after the first squaring, the input to the next operation is the same. So when I do the second squaring, I'm now squaring the same value, not different values. Now I got the same output at this point, between the s and the m. Now I'm taking the same value in the two exponentiating. In one case I'm multiplying it by x, and in the other case I'm multiplying it by minus x. One of the operands is the same, the other is different, power consumption curves will look totally different. So at this point I get different values. One of them is some value, and the other one will be its minus. After the next squaring, the difference will disappear again. After the m, it will be reintroduced, another plus and minus. After the next s, difference will disappear, and all the s's afterwards will operate on the same input. So what can I conclude from this? All the multiplications m will have different power consumption curves. Every s which immediately follows an m will have different inputs, and therefore power consumption curve will look different, but the outputs will be the same because I squared, and the plus minus will become the same. And every other s, except the s that immediately follows m, will have exactly the same inputs and therefore the same power consumption curve. So, if we know all those equal s's between a sequence of equal ss and another sequence of equal ss, you just plug in m followed by s, m followed by s. So you know the complete sequence. That's very easy to do. Here is the experiment. I exponentiated x, I got this crazy form. I exponentiate minus x, I get this crazy form. Looking at it, you can say nothing about what's going on. But I'm going to subtract them. So if you subtract it without any signal processing, you get something which is a bit complicated, because there is some time jitter and some inaccuracies and noise. But if you apply low-pass filter to the test signals before you subtract them from each other, then you see that here the two power consumption curves in exponentiating x and in exponentiating minus x were very different. So even after low-pass filtering, they look different, but with low frequency. And if you subtract them and they had the same input, they will be almost zero, almost identical power consumption curves. So I read, this is an S, this is an S, and between them there are just M followed by S. So I can read the whole secret exponent by looking at power consumption curves. I hope this was clear. It's a bit technical, but it gives you the flavor of how a very, very strong crypto system such as RSA will give you no protection whatsoever if you are allowed to think out of the box. I'll finish with one more very recent attack, which I developed in November 2007. I call it a bug attack. And a bug attack is something which exploits errors in microprocessors. So bug attacks exploits a permanent systematic defect which operation in Microsoft Excel program, the result was slightly inaccurate. It was almost correct, but I had a few bits which are wrong. And this does not affect only Intel. Maybe Intel will be very, very careful in analyzing and testing its multipliers, but you know, there are Motorola and Texas Instruments and AMD and all the Japanese and Taiwanese smart card manufacturers. So there are many, many companies which might not be so careful with their designs. So it is quite plausible that some of the multipliers implemented on microprocessors will have small bugs in them. Normally you would say, okay, if the bug is so rare that it was not caught during the testing of the chip, it will not cause any difficulty. So very, very rarely a small error in the computation will be created. But what I'm going to show you now is that even the smallest possible error in a multiplier, for example in an Intel microprocessor, will be a total security disaster in the following sense. Assume that the next generation of Intel processors, which will be used in hundreds of millions of devices, many of which will implement the RSA crypto system, has the following tiny, tiny error. For one pair of integers, A and B, so A is a 64-bit input, B is a 64-bit input, and for only one pair of numbers A and B, the product A times B is computed slightly incorrectly. For example, only the least significant bit of the result is incorrect. So 64-bit multiplied by another 64 bits, you get a 128-bit result. The least significant bit is flipped. But only for one pair of numbers. No one will ever notice it while running normal programs, because it happens only in 1 out of 2 to the 128 cases. You run random inputs. Okay, so doesn't sound dangerous, right? So it cannot be detected experimentally. You can run forever trying to find such A and B, you'll never find it. But assume that the NSA, I'm using them as the bad guys all the time, secretly discovers or asks Intel to place a bug in the multiplier. So they know, NSA knows what are those two numbers, mystery numbers A and B, which are multiplied incorrectly. We will show now, in the next 2 or 3 minutes, that any such multiplication bug can break all RSA keys on all the computers using all the implementations of RSA, using only a single chosen ciphertext. So there are going to be hundreds of millions of PCs, and the NSA will be able to break any RSA key on any one of those hundreds of millions of computers if it only wanted to, using one chosen message. So how can it operate? So here is one way in which the NSA could achieve this. So I'll tell you how it chooses the magic input X that it asks the target computer, please raise it to the secret power D. So now here I'm going to lose those of you who do not know much about RSA, because I'm going to depend on some properties of RSA. So those of you who are not experts in RSA, please forgive me. Try to follow it, but it might be a bit tricky. So knowing the public key N, which is the product P times Q, P is a big prime number, unknown, Q is a big unknown prime number. The NSA can easily compute a number, C, which is guaranteed to be between P and Q. So if you know P times Q, which is N, square root of N is a number which is guaranteed to be bigger than P and smaller than Q. Because if you multiply 7 times 11, and you get 77, square root of 77 is between 7 and 11. Let's say be the square root of N, rounded to the nearest integer. Any number which is sufficiently close to this square root of N is also likely to be, with very high probability, will be between P and Q. Bigger than P, smaller than Q. So the NSA will calculate a number which is the square root of N. And remember that A and B were the two magic numbers which are multiplied incorrectly. Each one is a 64-bit word. So it will plant in some of the lower order parts of square root N. In one word it will put A, and in another word it will put B. It doesn't matter exactly where it puts them. So this is very, very close to square root of N. So it's a number which is between P and Q, and it has a block representing the number A, magic number A, and it has another block which represents the magic number B. Now, the NSA uses this number as the chosen ciphertext and asks the device, please decrypt it for me. So the first step in Chinese remainder theory version of RSA, so if you use the Chinese remainder theorem, you calculate separately mode P and separately mode Q. So, since X, this half-size number, is bigger than P, but smaller than Q, the first thing you do, you take it and reduce it mode P, but it is, this number is bigger than P, so some randomization will happen. You will subtract some multiple of P out of it. But because this half-size number is smaller than Q, when you reduce it modulo Q, no modular reduction will happen. It is already reduced modulo the bigger Q. So, you get a situation in which this will remain exactly the same form when reduced modulo Q, but will be randomized, and most likely A and B will disappear when reduced modulo P. Okay? Let's continue. Each exponentiation always starts by squaring the input. Remember, square, multiply, square, 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 multiply, etc. First step is always square. So, the squaring is almost certainly going to use the natural division to divide it into 64-bit, another 64-bit, 64-bit. And when I square the number, I take every block of 64 bits and multiply by any other block of 64 bits. So in particular, modulo Q, this was the form of the number, and there was a block of A, there was a block of B. So when you multiply them, there was some mistake made. So the result of squaring is going to be slightly incorrect. When you do the first squaring of this number after it is randomized modulo P, the number is going to look different. It will not have A, it will not have B, it will not make any mistake. So the computation modulo P will be done correctly, the first squaring. The squaring modulo Q will have an error in it, some small error. After that, you do further multiply, square, square, multiply, but all of them will not have either A or B, so all the rest of the computation will be done correctly. But starting from an incorrect value, you end up with an incorrect value modulo Q, whereas modulo P, you do only correct calculations. How do you finish now? So, given the answer Y, and knowing the public exponent E in RSA, the NSA can take the decrypted plaintext Y, raise it to the power E, subtract from it the chosen ciphertext X, reduce the result mod N. For those of you who don't know RSA, forget what I said now. The point is that this value is a number which is 0 modulo P because it was calculated correctly. You're doing decryption followed encryption followed by decryption, so you calculate everything correctly mod P, so it is 0 mod P. Whereas modulo Q, you have made a mistake, so it will be non-zero. And now, you just calculate the GCD of this greatest common divisor. This value is L, and it is very likely to give you the secret factorization of the number N. So one chosen message is enough in order to break the crypto system. So I assume that some of you who work for various organizations are going to rush now to the laboratories and look at all the chips that you are using on your PCs and try to find if anyone planted any pair of numbers A and B, 32-bit numbers or 64-bit numbers, which are multiplied with any error whatsoever. Because any such multiplication bug means that your system is totally insecure. Can be broken with a single message. Let me stop. Thank you very much.
And today, Professor Shamir told us many new techniques about how to use the computer technique to deal with the secret key efficiently. Any question? Is there any question?
Yes.
Mr. Professor Shamir, I have a question about the example about the core boot attack. As you know, the AES cipher and some other block ciphers, the round key can be expanded on the fly. That's to say, I can expand the round key and store only one round key in the random RAM. My question is, do you think the core boot attack will be more difficult if I use the on-the-fly key expansion? Thank you.
So, first of all, most people who implement disk encryption are actually expanding the key because you do it once and then you use it for many, many blocks of data. The on-the-fly expansion technique that you mentioned means that every time you write to the disk, you have to spend extra time to expand the key and then do the encryption of one block of data to the hard disk. So it is much slower for the user. That's why most people actually expand the key. Now, suppose that somebody did not expand the key. So this will certainly complicate the attack, but will not prevent it. What should you do? Remember, there is a 1 gigabyte of RAM which was dumped into the USB token, the disk on key, and now, whereas the expanded key will enable you to quickly find where is the real AES key, now you'll have to try 1 billion positions, each one, so being a candidate for a key. So you look for the first block of 128 bits. You try to do a trial decryption, see if it works. If it doesn't work, you move your window of 128 bits and try the next one. So it will require 1 billion attempts, which is still doable. But this is assuming that there were no errors. Now let's assume that you are very fast in rebooting the device, but, 5 bits got corrupted. So when you look at all the windows, for each location of 128 bits, you also have to try all the ways how to flip up to 5 bits in the window. So it will not be just 1 billion keys, maybe, 2 to the 40 keys or 2 to the 50 keys. So it gets more complicated, but it will not stop the attack if you are fast enough in doing the analysis.
USB interface when encryption machine is worked with maybe a USB interface at the same time. When encryption machine is working, the power consumption will be always shielded or must to find the encryption key in the encryption machine.
Okay. So maybe there was a misunderstanding, but when I talked about the USB which is plugged into the device, it is not a normal USB. It is a USB prepared specifically, which doesn't consume any power. It only measures the voltage and records it, performs analog to digital conversion, and records the signal in the memory of the USB. So there is no power consumption on the USB itself. It measures the variations in the power supplied on the USB port, which is influenced only by the operation of the PC itself. So the USB that the attacker is plugging in is not influencing the power consumption, because it is specially prepared in order to just record the voltage available on the power pin.
And the second question is about your RSA algorithm.
Yes.
And I couldn't understand the power consumption between S and M. You mean that's the new types of implementation in RSA algorithm? The timing, the time consumption in S and M is almost the same.
The time is exactly the same. You use exactly the same algorithm.
Because the advanced encryption system have considered the power analysis. So the time is, and your analysis...
But I'm not using timing analysis. So maybe I will go back and explain this in a better way. 1 second. Okay. So this part explains the basic idea, namely, if you look at the details of a multiplication of 2 1,000-bit numbers, you have a 1,000-bit number and I multiply it by another 1,000-bit number, then if in 2 multiplications I'm using exactly the same inputs, the power consumption curves will look very, very similar, except up to noise. If I'm multiplying different numbers, then the power consumption curves will look different. So this is the basic assumption. Now what you are doing is the following. You are looking at an input which is x and minus x. Let's assume that x is 17 and minus x is 50. Okay? So in this case I'm exponentiating 17. In this case I'm exponentiating 50. So the operation here is squaring 17, or it is squaring 50. Power consumption curves will look very, very different. But because the inputs were x and minus x mod n, when you square x squared or minus x squared, the minus disappears. In both cases, the result is the same x squared modulo n. So the next squaring operation starts from exactly the same value, say 37. So here, the first squaring used 17 and 50, so it looks very different. But the next square afterwards is squaring the number 37 in both cases, so the power consumption curves will look the same. So that's the basic idea.
Can we recognize it by the power spectrum density?
You can recognize it either in real time or by the spectrum. It doesn't matter. Both methods work very well. But the point is that both in real time and in the frequency domain, it will look the same if you operate on the same inputs and different if you operate on different inputs. How you measure it doesn't matter.
Thank you very much.
There was a question here. Just behind you.
Good afternoon, Professor Shamir. I have two questions about insular factory. 1 year at a cost of less than $10 million.
This was an estimate from 2005.
Related to something like about physics, like say voltage or photons and microprocessors.